Hello, everyone. So this video here is going to be derivatives of trig functions, and I think it's really good just to start off with the two easiest functions that we know when it comes to trig functions, which is going to be this first curve, which this is y equals. Let me change my marker here real quick. I'm sorry. Okay, so this is going to be, instead of y, I'll use f of x equals sine x. And then if I scroll up, we got h of x equals cosine x. Okay, so if you remember in the previous video about taking a graph of a function and then finding the graph of its derivative, we're going to do the same exact thing here. So you could see that I have sine x in the top and cosine x in the bottom. Most importantly, I want you to look at that point, this point, and this point right here, because at those points, that is where we're going to have horizontal tangent lines, which means if we were to graph the derivative of sine x at these points, we'll call them A, B, and C respectively, we should be crossing the x-axis on its derivative curve. Well, it just so happens that if you come straight down, notice that you have every single one of those points right there on the x-axis of the cosine curve, which should go to show you that the derivative of sine x is equal to cosine x. Now, you can do the same exact thing for every single one of these trigonometric functions, okay? So what I want to do here is just kind of write them all out for you. So we have our derivatives of trig functions, and I will say this from the very start. I'm going to put a little star because these are, I don't want to say special cases, but until we learn this thing called the chain rule, this is what we have right here, okay? So the derivative of sine x is equal to cosine x. We just verified that. Now, the derivative of cosine of x is negative sine x. Like I said, all you gotta do is just graph it, and you will visually be able to see that. The derivative of tangent x is secant squared x. The derivative of cosecant x equals negative cosecant x cotangent x. The derivative of secant x is equal to secant x tangent x. And finally, the derivative of cotangent x is equal to negative cosecant squared x. So you don't hear me say this a lot, but it is in your best interest to go ahead and memorize these. So, like, for example, the derivative of tangent x is secant squared x. Well, let's see why, okay? So we are going to have to remember all of our trig functions that we learned a while ago. So if you need to, get out a trig book. I'm going to upload kind of like a little trig review thing. It's going to be very small though, okay? So make sure you go back and you verify like the Pythagorean identities, the double angle formulas, stuff like that. So the derivative of tangent x is equal to, well, let's think of it this way. We know tangent is sine over cosine, okay? Now, if I wanted to take the derivative of sine over cosine, I got to use my quotient rule. So the quotient rule is going to be cosine of x multiplied by the derivative of sine x minus, make sure you put that bracket there, sine x times the derivative of cosine x. Oh, let me put that in parentheses. There we go. All over cosine squared x. So I'm hoping you can kind of see what's happening here. Now, in the numerator, the derivative of sine is cosine minus bracket sine x, and the derivative of cosine is negative sine. All over cosine squared x. Now, cosine x times cosine x is cosine squared x, plus sine x times sine x is sine squared x, all over cosine squared x. According to the Pythagorean identity, cosine squared x plus sine squared x is equal to 1. And according to basic trig functions, 1 over cosine squared x is secant squared x. So that is how we derived the derivative of tangent x. And like I said, you can do this for every single one of these trig functions. It's very straightforward. You just got to remember all your trig identities. And that's kind of what makes this difficult. Now, I will make a note about this. We will be using radians. So make sure your calculator is in radians, okay? Also, use exact answers. So if the answer is pi, write pi. Do not write 3.14. That is not good, okay? Because 3.14 is an approximation. We need the exact answer, and the exact answer would be pi. Finally, I do want to go over a couple limit identities. This will help you out later on. The limit as theta approaches 0 of sine theta over theta is going to equal 1. And the limit as theta goes to 0 of cosine theta minus 1 over theta is going to equal 0. So with the remaining time, I just want to do just a bunch of examples of taking trigonometric derivatives. So let me write directions real quick. Find the derivative for each problem. Okay, so here's our first example. F of x equals x squared sine x. This, we're going to have to use a product rule. So there's f, and there's g. So f is going to equal x squared. F prime is 2x. G equals sine of x. G prime equals cosine x. So we got f prime g plus, f g prime plus f prime g. So all I'm going to do is just come directly underneath and just make my substitutions. F is x squared. G prime is cosine x. Plus f prime is 2x times g is sine x. So there's our first derivative there. Next one I'm going to do. F of x equals x cosine plus 2 times tangent x. So you got to be careful here because once again, if you look at the very first term, you're going to have to use the product rule here. All right. This second term is just taking the derivative of tangent x. So our derivative is going to equal x times negative sine x plus cosine x times 1 plus 2 secant squared x. And then when you clean this up, all right, you're going to get, I'm going to put the cosine x out front, minus x times sine x plus 2 secant squared x. So don't forget, with this term right here, highlighted in green, all right, you're going to have to use your product rule there. All right, so that's a product rule. Okay, next one. Let's look at y equals secant theta tangent theta. All right. So once again, product rule. Now this one I'll write out for us. So F equals secant theta. G equals tangent theta. Now the derivative of secant theta is going to be secant theta tangent theta. The derivative of tangent is secant squared theta. Remember, your product rule is f prime g plus g prime f. So y prime is going to equal f prime times g. So we get secant theta tangent theta, that's f prime, times g is tangent theta, plus g prime is secant squared theta, times f, which is secant theta. Now from here, we got to be careful, all right? Because what we want to do is try to simplify this in some way. So if you notice, in both scenarios, I can factor out secant theta. So by doing that, that's going to give me secant theta out front times tangent squared theta plus secant squared theta. And using the identity, secant squared theta equals 1 plus tangent squared theta. We can go ahead and rewrite this as y prime equals secant squared theta times 1 plus 2 tangent squared theta, or using this identity again, you could say tangent squared theta equals secant squared theta minus 1. So, or another answer could be y prime equals secant theta times secant squared theta minus 1. In other words, both of these answers are completely acceptable. It all depends on how you want to rewrite this, okay? All right, so let's look at a word problem. So we have a mass on a spring that vibrates horizontally on a smooth, level surface as shown. Now, the words smooth and level surface actually mean a lot to us here because we are ignoring friction altogether, all right? So just ignore friction. So this is like a perfect scenario. So right here, this big block is our mass. All right, it is at some position x. The equilibrium point is at 0. So if I were to pull back on this mass and let it go, we know that it will oscillate back and forth, and we can measure that oscillation with its equation of motion, which is x of t equals 8 sine t. So we know that the amplitude is 8, so this is just going to oscillate back and forth like this, and it's going to be there forever, just moving back and forth perfectly, okay? If you want to figure this question out by including friction, take my differential equations course, because we will be looking at situations where we do not ignore friction or air resistance. And those equations actually are not too difficult. They are second order, homogeneous, linear, constant coefficient differential equations. So that's a mouthful if you want to say it 5 times fast, but that's what they are. So anyways, so there are multiple parts to this problem, but I'm going to do part A, then we'll do part B. And it's actually not difficult at all once you see it. So once again, we got a mass that's on a spring vibrating horizontally on a smooth level surface. As shown below, its equation of motion is x of t equals 8 times sine of t, where t is in seconds, x is in centimeters. Part A, we just want to find the velocity, and then we want to find the acceleration at any time t. So we know x of t equals 8 sine t measures our displacement. Therefore, the derivative will be our velocity. So the derivative of sine t is cosine t. And this is our velocity. So very straightforward, nothing too crazy, okay? So I'm just going to rewrite this as v of t equals 8 cosine of t. And I'll put like a little box around this. I'll put a little box around the displacement. Now we know the derivative of velocity is going to be our acceleration. So we just got to differentiate 8 cosine of t. And remember, the derivative of cosine is negative sine. So this is going to be negative 8 sine t. And right there is our acceleration. And part A is done. Part B says, find the position, velocity, and acceleration of the mass at time t equals 2 pi over 3, and in what direction is it moving at that time? Okay, so like I said, if we look at this picture, we know that this mass is going to be oscillating back and forth. All right, what we want to know is where is it? What's its velocity? How fast is the acceleration changing? Or what is the acceleration at t equals 2 pi over 3? And in what direction is it moving at that time? So this is just, honestly, substitution, simplifying. That's it. So let's go ahead and let's do each one of these, separately. So the first, x of t equals 8 sine t. So this is going to be our displacement. We are asked to find x of 2 pi over 3. So we just go ahead and make our substitution here. Now recall that 2 pi over 3, or the sine of 2 pi over 3, if you use your unit circle, is going to be square root of 3 over 2. And then we can simplify this as 4 times the square root of 3. That is the answer you would type in. No decimals. Exact answers only. So here is x of 2 pi over 3. So I guess I'll just put like a little I there. Second, now we want the velocity. So the velocity at 2 pi over 3 is going to equal 8 cosine of 2 pi over 3. That is going to equal, if you use your unit circle again, the cosine of 2 pi over 3 is negative 1/2. And when you simplify 8 times negative 1/2, you get negative 4. Okay. And then the third part is going to be the acceleration. So we're asked to find a of 2 pi over 3. And that's going to equal negative 8 sine of 2 pi over 3. Now the sine of 2 pi over 3 again is going to be square root of 3 over 2. And when you simplify that, you get negative 4 square root of 3. Okay? And the last part of the question is, in what direction is it moving? So in what direction? Well, if we go back up here to our graph, my little picture that I drew, so I'm going to just copy and paste this real quick. There we go. Notice here, I wrote that as x, so that means the positive x direction is going to the right. And since my velocity at 2 pi over 3 is less than 0, meaning it's negative, this is moving in the opposite direction of right. So our mass is moving to the left. And that's it. So I hope this video was kind of informative. Finding derivatives, now that we don't have to use the definition of, the derivative, the limit as h approaches 0 of the difference quotient, finding derivatives is very simple. It's what we do with them. It's what they represent. Okay? So good luck. I'll see you in the next video.